All right, we're back again to discuss the El Nino La Nina patterns in wintertime. All right, so part 2 begins with this. All right, so as I was explaining at the end of the last video, part 1, with an El Nino pattern, this is what you have going on. You have a more active subtropical jet stream, this little red line right here. And what that does is that tends to generate a lot more storms further south over the Gulf Coast states. So you typically get wet and cooler conditions, mainly because you have a lot more storms in the wintertime, anywhere from Texas to Louisiana, the Gulf Coast states, Mississippi, Alabama, Georgia, and Florida. And of course you have an overcast sky condition when it's raining with these storm systems, so it tends to keep the temperatures cooler than average during the winter during El Nino. Further to the north, again, I was explaining this warmth that extends from Alaska down into western Canada, Pacific Northwest, the northern Rockies. And then the polar front jet stream with El Nino tends to remain fairly far to the north. So we really don't see this huge dip in the jet stream over the eastern US. So the cold air remains fairly far to the north for the most part, the main brunt of it. With a La Nina pattern, now take a look how things change. The areas that were wet and cool in the southern US and the Gulf Coast states during El Nino are now dry and warm. The Pacific jet stream here, the subtropical jet, tends to move more into the Pacific Northwest, which tends to make conditions wetter than normal for Oregon and Washington, for those areas, Seattle, Portland. And then we have a cooler area from southern Alaska down to western Canada into the northern plains states. And notice with La Nina, you do get a little bit further dip of the polar front jet, this purple line. It is a little bit more amplified into a trough pattern into the Midwest. So during La Nina patterns, the Midwestern U.S., we're going into a La Nina this winter, the Midwestern U.S. tends to be colder and snowier during La Nina patterns because of this dip in the jet stream. Storms tend to follow. They use this jet stream as a guide or a river. These are what storms travel along. So it's interesting to compare and contrast the two patterns here, El Nino versus La Nina, and the winter implications. All right, next oscillation we're going to get into is the Madden-Julian oscillation, MJO. And you wouldn't think that something that happens in the tropical Pacific, at the low latitudes of the Pacific, would have such a large impact on the weather here in our winter in the mid-latitudes of the U.S. But MJO, in fact, does have an impact. What is Madden-Julian oscillation? It's simply the major fluctuation in tropical weather on weekly to monthly timescales. And these fluctuations can be characterized as an eastward moving pulse of cloud and rainfall near the equator that typically recurs every 30 to 60 days. And that's directly from our friends at the Australian Bureau of Meteorology, BOM. So I do thank them, I do reference them at the end of this video as well. Tropical weather occurring at lower latitudes across the Pacific Ocean, again, can greatly impact the weather across the United States as the jet stream configuration changes form and the upper level winds change direction. All right, so MJO, let's take a look to see what really happens with the MJO. All right, keep in mind, I want to mention that this part here, that unlike the other oscillations, the MJO is characterized by phases, not by phase numbers, I should say, not so much by a positive or negative. They are represented by phase numbers 1 through 8. And they do have a direct correlation on our precipitation and temperature weather patterns in the U.S. So what happens here with the Madden-Julian oscillation, we're in the deep tropics of the Pacific Ocean. We have this is Australia, by the way. This is superimposed over a map. This is a vertical profile over India, over Australia. Over the Indian Ocean, basically, we have a lot of rising air motion, stormy and wet. Upward motion by this green arrow, building cumulonimbus clouds, thunderstorms, lots of rain. And then downstream of that, as the air rises, as soon as it reaches the stratosphere, it spreads out horizontally. And as it does, it eventually collides with air from the east, also at higher altitudes. When these two converge aloft, it results in sinking air or downward motion. So under this sinking air, you have sunny and dry conditions. And so this is almost like a cell that sets up. And realize too that it's eastward moving. So this is what the Madden-Julian oscillation is. It just shows you the different types of patterns, the upward rising air and the downward sinking air out in the tropical Pacific and even in the Indian Oceans. And it's amazing, this can actually impact our weather here. And this is how it impacts our weather here. Now, I'm showing you temperature composites of January, February, March over on the left here for phases 1 through 8. Again, MJO is divided up into phases 1 through 8. Here are temperature composites with 1, 2, 3, 8, 1, 2, 3, and 8. Those are typically characterized by colder than normal temperatures across the eastern U.S. 2 is actually across most of the U.S., indicated by the blue colors. Whereas phases 4, 5, and 6, and even 7 are warm, indicated by this orange and red colors. It's generally very much above normal as far as temperatures in phases 4, 5, 6, and 7 across the eastern U.S. And then you have on the right here significant percentage, January, February, and March, of precipitation, whether it's above or below normal. Generally, the brighter colors indicate more of above normal precipitation. The purple colors more of below normal. But I do want to mention that MJO phases and the weather to expect, again, this is January, February, March. I'm showing you more of a wintertime representation of MJO and how it impacts our temperatures and the actual precipitation. But it does vary on the time of year. So it does change. All right, so now let's take a look at some actual teleconnection analogs. And when I say analog, I'm talking about generally in the past what has happened with certain phases of the teleconnections. So on the left here I have a representation of January, February. Also on the right I have the same. And on the left I have an indication of the temperature anomalies. So this is showing you a positive AO. Yellows represent above normal temperatures. Green and aqua, the blue and aqua represents below normal. So with a positive AO in January and February, we have above normal temperatures in the east. However, if we turn that around and go negative on the AO, we have much colder conditions, mainly across the whole U.S. And there are representation of years up here. Shows you the years that these conditions actually happen with the different phases of the analogs as well. Now let's go to the NAO. Look at this, January and February teleconnections. Here's a positive phase of the NAO, where we're again milder in the eastern U.S. It's actually colder out in the Pacific Northwest, Northern Plains with a positive NAO. And then if we flip it in January, February to a negative phase of the NAO, again, the blues, the greens, aquas, they all represent colder than normal temperatures. So you see how you go from positive to warmer than normal conditions in the east to a negative phase of NAO and AO, and it's much colder. Now let's take a look at the PNA teleconnection analogs for January and February. In this case, if it's a positive PNA, right? With a positive PNA, you have milder or warmer, a ridge over the west and a trough in the east. Ridge in the west, trough in the east. So with a positive PNA pattern, you typically have colder than normal conditions in the eastern U.S. in the winter. And if it flips around and becomes a negative PNA, you generally have colder conditions in the west and milder conditions in the eastern U.S. All right, now we're going to take a look at an actual forecast here by the GFS model of the AO, the Arctic Oscillation, the North Atlantic Oscillation, and then the Pacific North American pattern forecast. So looking at this one line here on each of these diagrams, this one horizontal line indicates neutral conditions. So if you see blue tick marks above this line, this reference line, that means it's positive phase. If you see blue tick marks below this reference line, it's negative phase. So in this case for the AO, this is a forecast from now till basically this forecast is going to run out all the way through early November. We're expecting the AO to be more of a slightly positive. The NAO is also trending positive, then becoming slightly negative through over time. And then we're going to see the PNA. You see how sharply negative it was, how the magnitude, the longer the line, the greater the magnitude. So you see that we have a much more negative PNA pattern, and then it's becoming positive over time. Okay, so these change daily, they change weekly. Look at the MJO forecast. All right, we're sitting off. This is the actual over on the left here. We have the ensemble, GFS ensemble. And then on the right, this diagram indicates the operational GFS. But in either case, we start off right here in phase 5. So you see each of these little sectors represents a phase of the MJO. So we start off in phase 5, and then you follow the big thick green line over. You go from 5 to 6 to 7, all the way around into phase 1. Okay. Same thing over here, starting in 5, and you're working your way counterclockwise into phase 1. All right, so what are the forecast challenges with teleconnections? All right, I should emphasize that teleconnections can work against each other. For example, you could have a negative Pacific North American pattern, which would indicate a trough in the west, ridge in the east. You could have a negative AO, which would indicate a trough in the east, colder below normal temperatures and lower upper level heights. And then you can have warmer phases of the MJO, which result in, if they all cancel each other out, if they work against each other and they're equal and opposite in direction, that will generally result in seasonal weather. However, you can also have them all working together in one direction, whether it be warmer or colder, to produce anomalous or extreme weather events. All right, so for example, you could have a positive PNA, which would have a trough in the eastern US. You could have a negative AO and NAO, which would indicate troughing and below normal temperatures and storminess in the eastern US. And you could have a cold MJO phase, right? Or one teleconnection can be much more dominant than all the others. For example, in the winter of 2016-17, the MJO pretty much dominated over all other teleconnections. So there's still much more to learn about this phenomenon and how it impacts the planetary atmospheric circulation. It's very difficult to decipher the teleconnection forecast outside of ENSO and La Nina. We have a pretty good understanding of ENSO and La Nina with all the research that's been done in the past. All right, but exactly what the teleconnections are going to do over time in the long run, even in the medium range, remains quite a forecast challenge. Further research continues in this critical area, and it will lead to more accurate seasonal forecasting for a specific area of the globes. So, we're going to continue to work and do research on this area, but it is a challenge. All right, so here are the references I used. Madden Teleconnections is a great website to look at. The NOAA National Centers for Environmental Information, the NOAA Climate Prediction Center, the Australian Bureau of Meteorology, and the AMS Glossary.